The Champlin Refining Company, producers, refiners, and marketers of a complete line of quality petroleum products, presents Producing and Refining Champlin Oils, a story of the many hundreds of intricate and complicated processes raw crude must be put through before it becomes the rich, full-bodied lubricant that is used in your motor. The oil game, a phrase so commonly used, is hardly a true presentation of the nation's largest industry. The oil business is a scientific business, full of hazards and dangers. Through geology, the oil-bearing stratas are studied, mapped, and charted. The next step is the location of the drilling rig so as to pierce the heart of the oil pool, which oftentimes is 8,000 to 10,000 feet beneath the Earth's surface. Many times these locations fail, and the result is a dry hole, or if a portion of the oil-bearing sand is touched, the crude production is not sufficient to offset the huge expenditure necessary for equipment and labor. This diesel-electric powered rotary rig requires a 130-foot derrick and will carry a load of 535,000 pounds. The derrick, 24 feet square at the base, is mounted in concrete. In this process of drilling shown, the 90-foot length of 6-inch pipe are being lowered into the hole. Another 90-foot length must be fastened on, and this process continues until the bottom of the hole is reached. The bit is fastened to the first piece of drill pipe that enters the hole. Oftentimes, these bits last only during 2 to 100 feet when drilling through rock or any hard shale formations. The pipe must be pulled out of the hole and stacked in the derrick until the last one is reached and a new bit added. 2 350-horsepower diesel engines generate the electric power on this huge rotary rig. It is possible to drill the depths of 2 to 3 miles with a unit of this size. The Champlin Refining Company receives most of its crude oil from the Oklahoma portion of the rich mid-continent producing area. Crude petroleum varies in each region throughout the world. However, it is generally agreed that paraffin-based crudes are favored for the production of lubricating oils. One of the outstanding early oil fields was discovered in the capital city of Oklahoma. Champlin-owned pipelines gather this crude from the Oklahoma City field, from the rich area around Kanawha, Wewoka, Seminole, Lucene, Garber-Covington, and other Oklahoma fields, and it is pumped to the refinery, which is located at Enid, Oklahoma. Oklahoma crude is noted for its low sulfur content, and its paraffin base assures a rich, clean lubricant. The crude oil is transported through pipelines and pumped into the various storage tanks shown in the foreground. This is the West Champlin Tank Farm. In the background is the refinery. This refinery is one of the largest independently owned and operated plants in the world. It covers an area of approximately 100 acres, and 300 employees provide continuous operation of this plant 24 hours a day, holidays and Sundays, to ensure an adequate supply of a complete line of petroleum products. Loading facilities for tank cars are so arranged that 104 cars of refined products and fuel oil, 15 tank cars of lubricating oil can be loaded simultaneously. At the truck loading rack, 6 trucks may be loaded at one time with refined products through separate lines, thus avoiding contamination or mixture. Each line has its own accurate meter. Not only is motor oil made in this huge plant, but the various other byproducts, such as gasoline, kerosene, tractor fuels, greases, and distillate. This aerial view shows the East Tank Farm, which is used to store crude oil. In order that you may follow each of the complicated steps, an animated chart has been prepared along with these actual scenes of the refinery. By following the red arrows, we hope that you will be able to visualize the production of lubricating oils. From the storage tanks, the raw crude is pumped to the shell stills. This is the first step in the long process of raw crude oil through the Champlin refinery. There is a battery of 36 of these large stills, and the principle of their operation is the same as applying heat to a large vessel and allowing the lighter fractions or vapors to boil off. The lighter ends come off the fractionating tower at the top. These lighter ends, such as gasoline, kerosene, distillate, and gas oil, come off these fractionating towers, and from the reduced crude that is left, lubricating oils are made. These various products are separated according to their boiling points. pictured here in the first battery of stills, gasoline comes off at the fractionating towers at the top. On down the line in the next group, kerosene is removed. In the next group, distillate, and from the last group, gas oil. This heat is applied to the bottom of the stills, and under each of the stills is a large furnace, which burns a mixture of gas oil and waste sludge that is pumped from the other units throughout the plant. This reduced crude is taken from the shell stills, then to the vacuum still. A vacuum prevents heating the oil to an excessive temperature, and by the use of a vacuum, the correct heating can be gained at 750 degrees. If a vacuum were not used, it would be necessary to heat to at least 900 degrees. This would tend to scorch and cause a larger deposit of carbon in the oil. In the large furnaces shown in the lower part of the picture, the reduced crude is heated to a temperature of 750 degrees. Steam is admitted to this still to prevent any possibility of the oil being scorched. After it has been heated and vaporized, the oils and vapors are distributed into the vacuum column. When they enter the column, the undesirable elements naturally present in the raw crude, such as tar, carbon, and so forth, immediately drop to the bottom, leaving the bright stock or cylinder stock. The wax distillate, which is composed of the lighter ends and from which neutral oils are manufactured, is taken off at the top of the tower and fractionated by pumping the cool oil into the top of the tower and allowing it to run down gradually over bubble trays inside the vacuum still. This produces different cuts of various grades of processed lubricating oils, which are used for manufacturing finished lubricating oil. The bright stock is drawn off at approximate middle of the tower and is then pumped to the agitators for special treatment with sulfuric acid. During each step, the laboratory runs strict tests to be sure of the quality of the lubricants. The oil is pumped to these agitator towers where 30 pounds of acid is allowed to 1 barrel of oil. When the acid is admitted to the oil, this agitator is full, and compressed air is added to be sure that the acid comes into intimate contact with the oil. After the acid and the oil have been thoroughly mixed, the air is shut off and the agitator allowed to stand, permitting the sludge to settle to the bottom of the tank. This sludge, consisting of carbons and tar substances, is drained off into these large sludge kettles and is mixed here with heavy fuel oil and is burned under the stills and boilers through the plant. After being treated and purified with the acid, the oil is then taken to this building, which is the contact plant, and filtered through finely ground clay of 200 mesh. This clay is as fine as talcum powder and highly alkaline, which neutralizes any sulfuric acid that may have been left in the oil as it came from the agitators. A gallon of oil is allowed to a pound of clay. This mixture of oil and clay is then heated in this large furnace to a temperature of never more than 525 degrees. This reduces the viscosity of the oil so that the clay will come into more intimate contact and absorb all the acid or solid matter that may be left. It is then pumped into tanks where it is mixed with naphtha of from 45 to 47 gravity. This is done to again reduce the viscosity of the oil and make the mixture more fluid. It is then taken to the Sweetland presses where all of the clay that has been used in these various processes is removed from the oil by pressure and steam. The oil is forced through layers of canvas, and this canvas serves as a filter which stops the clay, allowing the oil to go on through. After the canvases become full of clay, it is necessary to take out these canvases and remove the clay that has collected. Shown here is the Sweetland press being closed after removing all of the clay. The oil is then pumped to these solution tanks where more naphtha is added. The oil is then heated to approximately 135 degrees in the solution tanks. This is done to clear up the mixture and to thoroughly mix any additional wax that may be hanging in suspension. It is then pumped to a cold settling tank where it is slowly cooled. The mixture at this point is approximately 30% oil and 70% naphtha, and as it is cooled to a temperature of approximately 35 to 40 degrees below zero, Large paddles keep it continually turning and mixing so as to keep the wax and oil in suspension. The purpose of placing the mixture in these cold settling tanks is to slowly cool it so the mixture will not be shock-chilled before being pumped into the chilling towers. The chilling solidifies the wax to a certain extent, yet it keeps it in solution, and it is much easier to remove the wax when it comes into contact with the centrifuge machines. The mixture is then pumped from the cold settling tank into the chilling towers. In this battery of chilling towers comes the first step in the dewaxing of Champlin oils. These towers are insulated with 10 inches of compressed cork to prevent any loss of refrigeration. The mixture is pumped from one tower to the other, and the oil is cooled at the rate of 2 degrees a minute. It goes into the first tower at 30 degrees. In the second, at 15 degrees. The temperature in the third tower is 0. In the fourth tower, the temperature ranges 15 degrees below 0. In the fifth unit, at 30 degrees below 0. And in the sixth tower, the thermometer shows 40 degrees below 0, which is the assurance that Champlin oils will flow freely at low temperatures. After this series of dewaxing processes, the oil is pumped to the centrifuge machines. A centrifuge machine operates on the same principle as a cream separator on a farm. Cream has a lighter gravity than milk, and it is easily separated when subjected to this high-speed whirling process. The same principle is applied to oils. The petrolatum, or the heavier ends of the solution, are drained off at one spout, while the lighter ends are drained off at another opening. Hot water is pumped into the centrifuge machines at a temperature of 140 degrees. The purpose of the water is to act as a carrier for the petrolatum. Petrolatum has a melting point at 140 degrees. These centrifuge machines are another step in the thorough dewaxing of Champlin oils. The oil at this point is pumped to the shell stills for more heating. While heat is being applied to the bottom of the still, a blanket of steam is added through perforated pipes to prevent scorching. This heating process removes the naphtha. The temperature is closely regulated and not allowed to go any higher than absolutely necessary to distill the naphtha off the bright stock. The bright stock is then pumped into storage tanks. However, it is not considered completely refined at this point because it must go through a series of filters. This takes many weeks, as this process of filtration through finely ground fuller's earth must thoroughly remove any small particles of wax or other undesirable items left in the oil. These huge tanks hold 13 tons of this fuller's earth, and here new clean earth is being put into the tanks. 2 stories down in the bottom of the building is the lower end of these tanks, and the oil has passed through the fuller's earth and through finely woven cloth and cotton. As the valves are opened, bright stock, rich in color, full-bodied in lubricating qualities, flows into storage tanks ready for blending. The purpose of filtering it slowly through fuller's earth is to neutralize any acids and to remove carbons and rosins. We have taken the bright stock through its various processes, and we go back now on the chart to the vacuum still, where we take up the various processes that the wax distillate must go through before it becomes finished neutral oils and used for blending with the bright stock to get the proper SAE grades. The wax distillate is the lighter ends that have come off the vacuum still, and the first process takes us to the chillers, where it is cooled down to 30 degrees Fahrenheit after the terrific heat that has been applied in the vacuum still. It is then pumped to the wax presses. Here is one unit of 4 wax presses, which is the final stage in dewaxing Champlin oils. The oil is pumped into these presses, forced through filters at a temperature of 35 to 40 degrees. As the wax solidifies, the oil drains into insulated tanks below. Note the oil dripping from frost-covered filters. The oil is put through a series of 2 of these wax presses and chillers. The last press is kept at a temperature of 0 to 5 degrees below zero. This double process assures a high percentage of wax removal. Also, the removal of other undesirable elements naturally present in the oils. Periodically, it is necessary to clean these presses and remove all the wax. This crystalline wax is then taken through another series of refinement processes which make it available for commercial use, such as candles, wax paper, and so forth. Wax is naturally present in all paraffin-based crude oils. However, it has no lubricating value. The Champlin Refining Company is one of the pioneers in dewaxing processes for the improvement of the lubricating value and reducing the cold test of high-quality lubricants. From the wax presses, the oil is taken to the pipe stills, and at this point the Champlin Refining Company is using a new and improved method in the processing of oils. It is called the pipe still process with fractionating column. The pipe still process consists in the main of a furnace for turning the liquid crude into crude vapor and a fractionating tower where the vapors are allowed to cool and settle into the different sections of the tower according to volatility. In the past, the old shell still process was used. Here the distillate was pumped into the still and direct heat was applied, which boiled the lighter fractions off. This process required from 30 to 35 hours of continuous heating, and it was found by the application of this extreme heat for such a long period of time directly to the bottom of the still, there was a tendency to scorch and overheat the oil, cutting down on the quality. From the wax press, the pressure distillate is first pumped to the top of the column and goes in at 40 degrees Fahrenheit through a series of coils and comes out again at 260 degrees Fahrenheit. It is immediately pumped to a furnace, which again heats this mixture by an indirect fire to 750 degrees. It enters the bottom of the fractionating tower, and this entire process of heating to this point takes less than 33 minutes. As it enters the tower, the lighter ends vaporize up through the bubble trays to the top of the fractionating column and are taken off at 350 degrees Fahrenheit. These vapors that are passed off at the top are the lighter ends and are immediately pumped into a cooling condenser and are transferred into storage tanks. This is what is called gas or furnace oils. Midway up the column, 100 oil is taken off and is pumped to a smaller fractionating tower, then a cooling process, and then into storage tanks. At the bottom, 240 oil, or 20 SAE, is taken off the smaller tower under 750 degrees temperature. Then from the smaller tower to a condenser coil, where it is cooled to a temperature of 140 degrees. It is then transferred to storage tanks for further treatment in the acid agitators, which is a similar process of purification as used for the bright stock. As the 240 oil is pumped into these acid agitators, compressed air and sulfuric acid are added, and the oil and the acid are allowed to be thoroughly mixed until the acid has gathered all the impurities in the oil. The impurities that the acid separates from the oil drop to the bottom and form a sludge, and are drawn off and burned in furnaces and boilers in other parts of the plant. The oil is then drawn from this agitator and pumped to a second agitator, where it is mixed with weak caustic soda, which acts as a neutralizer for sulfuric acid. Air is added to this second agitator so that the acid and alkali will be thoroughly mixed. After it has been tested and found to be on the alkaline side, it is then pumped into a bleacher, where it is cooked with live steam until it reaches the temperature of 180 degrees. Steam cooked into the oil causes moisture, and the moisture weakens the alkali, allowing it to drop to the bottom of the bleacher and is drawn off as waste. The live steam also tends to neutralize the acids and the caustics. At each stage in this process, samples are taken to the Champlin laboratory and given tests to be sure it is neutral, not acid or alkali. After this stage of purification has been completed, it is taken to the filter house. It takes weeks to allow the oil to filter through these 24 large units. After the oil reaches this stage, it is then a finished product and ready to be compounded or blended with bright stock to make the various SAE grades. The viscosity test is the measure of the body of the oil. Heavy-bodied oil is high in viscosity and is slow pouring. Shown here is the Seibolt Universal Viscosimeter, and the viscosity reading is taken in Seibolt seconds of the time required for 60 cubic centimeters to flow through the standardized opening at a constant temperature. Another important test is measuring the gravity of the liquid petroleum. The API hydrometer, carrying an arbitrary scale when allowed to float freely in oil or other liquids, sinks to the depth corresponding to the density of the liquid. The gravity value is then read at the point where the surface of the liquid intersects the scale. The pour test of an oil is the lowest temperature at which oil will flow or pour when it is chilled without disturbance under certain definite specified conditions. Champlin Zero pour test motor oils are famous for their ability to flow freely at low temperatures. These are only a few of the many strict tests Champlin oils must undergo before they are sent to the barrel plant to be sealed in 1 and 5 quart cans or barrels. This canning machine can fill as high as 90 quart cans per minute when running at top speed. These cans are filled, weighed, sealed, and packaged, 24 to a carton, all done in practically one operation. It is then an easy matter to set them on automatic conveyors to other parts of the barreling plant for storage or to the loading platform for shipment. The Champlin Refining Company makes a complete line of greases, and these are put up in handy containers for farm use. This operation shows greases being packed in handy half-bushel pails. Important are clean, freshly painted barrels when oils are delivered to the customer. After being thoroughly scalded inside and out, these shiny new barrels are quickly painted with bright Champlin red and set into the oven, which bakes the paint to a shiny finish. The barrels are then sent on automatic conveyors to the floor below, where they are filled with the various SAE grades and sealed according to orders. Each batch of oil, as it is blended, carries a number, and each batch is thoroughly tested before being sealed in drums or cans. Here in this barreling plant are all the modern facilities for packaging Champlin greases and motor and tractor oils. The building has a total floor space of 30,000 square feet and is one of the new and modern additions to the Champlin Refinery. The Champlin Refining Company operates a fleet of these huge trucks, which are constantly on the road, delivering shipments to terminals at Hutchins in Kansas, Superior, Nebraska, Rock Rapids, Iowa, to warehouses in Denver, Colorado, Grand Island, Omaha, Nebraska, Mason City, and Cedar Rapids, Iowa, Fulton, Missouri, Oklahoma City, and Amarillo, Texas. On the road, these trucks preach and practice safety, and the brightly painted vans broadcast the message of Champlin quality. By going back and thoroughly checking every process shown in the manufacturing of Champlin motor oils, You will find that this lubricating oil has been made rich in quality due to the fact that by thorough tests and scientific refinement it meets the rigid specifications of present-day requirements. Champlin lubricating oils are offered to the motoring public on merit alone. Quality has not been an adjective coined in the abstract to describe these oils, but it has been put into each stage of refining. Champlin oil has been standing up under heavy tests for nearly a quarter of a century and proved itself to be an oil that can take it when the going is tough. For safety's sake, insist on good oils in your motor, and for safety's sake, when driving on the highway, heed the message on each Champlin signboard throughout the Middle West, and remember, safe driving has no substitute. The Champlin sign is your guarantee of quality.